Hi everyone, my name is Chang Fei from Keysight. The topic of my sharing today is achieving minimal transmission loss in coplanar waveguide with 100 GHz bandwidth for millimeter wave communication. The content of sharing for today is the intro of millimeter wave and followed by analysis and result optimizing the coplanar waveguide or CPW design, followed by summary. Next, intro of millimeter wave. Millimeter wave is an EM frequency range below infrared. Its frequency spectrum is applied for high-speed telecommunication such as 5G and potentially 6G network deployments. Millimeter wave has a wavelength range from 10 mm at 30 GHz to 1 mm at 300 GHz. The wireless communication in millimeter wave band is speedy and low in latency, facilitating higher data rate versus the other telecommunication in lower frequency band such as the existing cellular networks. Comparatively, a millimeter wave network has enhanced data rate and capacity and does not travel and interfere with the existing neighboring cellular network system. Next, analysis and result, optimizing the transmission line routing for CPW. This is the top view of the CPW 3D EM modeling in EM Pro is shown in a figure on the right side. The signal trace and its side ground planes on the layer 1 has 1 ounce thickness, 7 mm trace width, and 4 mm coplanar gap, and 500 mm length, and laid 4 mm above the solid ground plane on layer 2 with the Macron 6 dielectric laminated between the two copper layers. The nominal characteristic impedance of the signal trace is 50 ohm, and the ground stitching via array on each side of the signal trace connecting the ground planes on layer 1 and layer 2 has diameter 10 mm. The dx is the center-to-center distance between the two adjacent vias, whereas the dy is the center-to-center distance between the via and signal trace. dx and dy are varied for 5 CPW models to investigate the effect of the ground stitching via position to the transmission loss, and then listed below. So we have A1, A2, and B1 and B2. So we vary from 15 to 30 and then 60 for each of them. So for insertion loss, according to the S21 plot above, the CPW model 1 with dy 15 mm experiences the smooth S21 curve without any resonant dip up to 100 GHz bandwidth. Whereas for A1 with a dy 30 mm, A2 with dy 60 mm, encounter resonant dip at 63 GHz and 32 GHz respectively. The quarter wavelength at frequency 100 GHz and 73 and 32 GHz on the PCB laminated with Macron 6 with DK 3.5 is about 16 and then 32 and also 49 mm respectively. And next for return loss, referring to the S11 plot above, the signal reflection is the lowest faced by the CPW model A, followed by A1, the highest for A2 throughout the wideband range up to 100 GHz. Next, for line impedance, referring to the TDR plot on the top, CPW model A experiences stable and smooth trace impedance around nominal 50 ohm, while model A1 faces slightly higher impedance fluctuation. A2 suffers the worst case due to the dielectric dispersion. Next, electric field profile for A1, A1 and figure on the left shows the electric field is localized around the transmission line for W model A, whereas for A1 and A2 encounter electric field that is more widespread. Non-localized electric field around the line causes the PCB substrate dielectric dispersion, which in turn contributes to the fluctuation of the line impedance that results in the worsening of the signal reflection and transmission loss. Next, the insertion loss. According to S21 above, model A experiences smooth S21 curve without any resonant dip up to 100 gig, whereas for B1 and B2 encounter resonant dip at 60, 76 and 32 GHz respectively. The wavelength at frequency 100 gig, 76 and 32 GHz on PCB laminated with Macron 6 DK 3.5 is about 16 mm and then 21 mm and also 49 mm respectively. Next, for return loss, referring to S11 plot above, the signal reflection is the lowest phase by the model A, followed by B1 and then highest for B2 throughout the wideband range up to 100 gig. Next, line impedance, referring to a DDR plot on top, the model A experiences stable and smooth trace impedance around nominal 50 ohm, while B1 faces slightly higher impedance fluctuation, and B2 suffers the worst case due to dielectric dispersion. Next, electric field profile. Figure on the left shows that the electric field is localized around the transmission line for model A, whereas B1 and B2 encounter electric field that is more widespread. A non-localized electric field around the transmission line causes PCB substrate dielectric dispersion, which in turn contribute to the fluctuation of the line impedance and result the worsening of the signal reflection and transmission loss. Signal transmission line also serve as a EM radiation source that emit EM wave outward and with approximately quarter wavelength. The electric field is more localized in CBW with more closely positioned ground stitching vias that help to minimize the electric field radiation, spurious coupling, signal reflection, and dielectric dispersion. Hence, CBW model A with DX and DY 15mm, which is below quarter wavelength, is built for 100 gig. Next, optimizing the footprint geometry joining the end launch for CBW. Model A is attached with an end launch connector depicted in figure above and labeled as model C1. The connector has 110 gig bandwidth. Meanwhile, footprint geometry joining the end launch for CBW is trimmed in two shape patterns, model C2 and C3 shown below. And then line impedance, referring to a TDR plot on top, model C1 without trimming the shape encounters capacitive impedance discontinuity 3.25 ohm, while the capacitive impedance discontinuity is experienced by a C2 with trimmed triangular shape of footprint is reduced to 2.4 ohm. On the other hand, C3 with trimmed trapezoidal shape footprint faces capacitive and inductive impedance mismatch 2.9 ohm and 1.7 ohm respectively. The trimmed triangular shape is better designed that minimize the impedance mismatch. Next, insertion loss. S21 plot above indicates that the transmission loss for C2 is the lowest across the wideband, about minus 1.19 dB at 100 gig, versus the other two connector footprint shape patterns due to the smallest impedance mismatch experienced by the model C2. Summary: this paper has provided an overview of the millimeter wave frequency range used in 5G and 6G telecommunication and presented a study that alleviated the transmission loss for CBW with 100 gig bandwidth applied on the PCB. By optimizing the position of the ground stitching vias with 15mm and or sub-quarter wavelength separation and the trimmed triangular shape of the trace and launch for the CBW with 500mm length, the insertion loss is held below minus 1.2 dB without significant resonant dip up to 100 gig bandwidth. That's all for my sharing. Thanks.